For homework this week, I want you to read Chapter 2 in Core Java for the Impatient. I want you to start looking at Section 1.3 of the textbook. That's where we'll start talking about stacks and linked structures. We'll start that next week. And in particular, look at the subsection on linked lists, which starts around page 142. It's sort of toward the back of Section 1.3 of the textbook, but we're going to start there. Talking about how link structures are built. And then I've got some homework for you on D2L that I'll walk through now. And let's just start looking at it. So here's my second homework. There's several problems that are marked in here with to-dos. So the first problem is to translate the following sum function from an iterative solution to a recursive one. So you should write a helper method. Don't use any fields to solve this problem. You're not allowed to do anything like this, where you declare variables outside the function. We'll talk more about that next week, but don't do that. And you're allowed to write a helper function for each recursive function. So here's the sum. You should write a sum helper. So I think I give you an example up here. Yeah, this something like this is a reasonable sort of helper function that you might work with and start working on how you want to figure out the sum function. I've given you a model, which is to figure out the minimum value. So here is the minimum value iteratively using a while loop, and here's the minimum value using a forward recursion. So here we're asking you just to compute the sum, and you compute it either using a forward or backward recursion. I encourage you to try both, actually. See if you can write it both ways. The second problem is to write a recursive version of the reverse function given here. So this is, again, something where you can write a helper function to get you through the list and figure out how to write this recursive function without a loop. So you're forbidden to use loops in these recursive functions. You should not have any occurrence of while or for. Those words should not appear. If they do, then you've got something wrong. For the next problem, you're going to be working with Mickey Mouse. I had to adjust my screen a little bit to get this to show. So when you run the program, it should pop up a screen that will draw Mickey Mouse for you. When you close that window, it will terminate your program. I was having trouble because in full screen mode on macOS, it appears that Eclipse will not show the Mickey Mouse window. So I encourage you to use Eclipse outside of full screen mode when doing this homework. So what's Mickey Mouse look like? Well, Mickey Mouse is essentially 3 circles. So I've given you code to draw 3 circles. And there's some stuff in here that I've put in to help you or to give you hints toward the solution of the recursive version. But what are we going to do? I'm drawing a circle for Mickey's head. I'm going to draw a circle for the left ear. I'm going to draw a circle for the right ear. If you want to have different colors here, that's fine. You can change. Let's make one ear green and one ear pink. Let's see if that works. Yeah, it seems to work. So I can run here and I'll get a green ear and a pink ear. Woohoo! So you can color Mickey if you like. Any case, what I want you to do is convert this code so that instead of drawing Mickey Mouse, we get Mickey Moose. So what's Mickey Moose? Mickey Moose is an example of a fractal. So fractals are very cool examples of recursion. It's essentially a recursive drawing. So here's an example online where the fractal is responding to my mouse. And you can see here another example of a fractal or a recursive drawing where, again, it's responding to my mouse. There's lots of such examples. This is probably the simplest one. You can think of a coastline getting more and more complicated as you get closer to it. You can see this is sort of recursively getting more complex. And a tree here. So these are fun things to mess around with. And these are all examples of recursive drawing. So recursive drawing is definitely amusing. Let me see if I can do this. I'm going to drag a square over here, and I'm going to use the Shift key to change the width of the square, and then use no Shift key to sort of shrink it a little bit. And I think I can move it. Yeah, I can move it down here. So I'll just have my little square, my rectangle. Then I can take it and drop. So what I'm doing here, notice I'm taking this picture and dropping it on itself. So this is saying I want to include the picture in itself. What you can do then is shrink the picture that you're adding. You can move it around. So, and I might move this a little bit that way, say. And you end up with something like this. And now I can drag the picture on itself again. And this is where it gets sort of amusing. You can edit this where you move the picture around. And like that, say. You get a nice little tree. This is a recursive drawing, so the drawing includes a sub-drawing of itself. And it's a rather amusing thing to play around with. I'm going to have you do a really simple version of this, which is to figure out how to convert Mickey Mouse to Mickey Moose. And the key here is to replace the drawing of Mickey's ears with a recursive call to the drawing of his head, just smaller. Right? So I've set this up for you so that all you have to do is adjust the positions and the radius. To give you an example here, you can see how I'm adjusting the positions and the radius in order to draw the ears. So think about it. Try to get your code as simple as possible. You should only need your recursive function to draw one circle. See if you can make that work. The next part of the homework is to run this function called terrible Fibonacci. This is terrible Fibonacci loop, which runs Fibonacci over and over and over again for larger and larger numbers. Just run it on your computer for an hour and see where you get. You can see here what's happening on my machine. When I get up to Fibonacci of 42, 43, it's pretty slow. I mean, the early Fibonaccis are really fast, but these later Fibonaccis are very, very slow. And after about an hour, I don't remember what I get up to, but it's not super large. So let me just terminate that. And that's the problem here is just for you to put a comment in here. All you do is write in what's the last number you got. So just write it in here. Replace the double dots or the triple dots with the numbers that you got after an hour of running it. The final problem is to actually rewrite the terrible Fibonacci to make it more efficient. So here you need to think a little bit, and you can think about in the lecture that I presented the two ways that we looked at the Fibonacci function. So one of them was the top down, where we had two calls to the terrible Fibonacci, but there was a way of thinking about this function in a tabular way where we started at the base case and worked up. So think about trying to implement it that way. Once you've successfully finished the homework, the output should look like this. You should have a lovely fractal Mickey Mouse, and in addition, you should have a notification that you've finished all the tests, and you should get a printout of the first 100 or so Fibonacci numbers. One thing I'll point out is that the Fibonacci numbers get so big that eventually they outrun the amount of memory in the machine that's used to store the value of the Fibonacci. And you can see on my machine, it's right around 92. I run out of room and something weird happens. At 93, they go negative. This is because of wraparound in the values. So once the values exceed the maximum possible value for integer values, they wrap around. I actually used a long to represent the return value here so as to delay this wraparound as much as possible. With an int, you only get 32 bits, which is about 4 billion values. Half of those are used for positive, half are used for negative, so you get up to 2 billion and you're done. At least here I'm getting up to about 8 quintillion. And so, but once you get around 8 quintillion, it's done and it'll go negative on you. Good luck with the homework.